Okay. So I'm Stephen Savage. I'm an academic. I'm currently a student at the University of Washington, soon to be assistant professor at UC San Diego. And as is de rigueur for assistant professors these days, I also have a company listed here that works in the denial of service space. And I've been invited to give a talk about what I know about the state of the practice and perhaps the future in tracing back IP packet streams. So for those of you who have been asleep for a little while, let me give you some context. About 30 years ago, some guys, anyone from BBN in the audience here? About 30 years ago, some guys at BBN got together and said, we're going to build the internet. It's going to be a great place. Our friends are going to play. It's going to be an environment of goodness and harmony and peace and love. And that worked pretty well in 1969. And these days, we have very much a different environment. And there have been ongoing attacks on e-business for the last several years, culminating this last March in some very publicized denial of service attacks that took down sites such as Yahoo and so forth. So the problem that I'm going to talk about today is flooding-style denial of service attacks, wherein an attacker overwhelms the network and CPU resources by sending spurious responses through the network, either overwhelming their network resources, using up all their buffers, or using all their CPU resources. And there are really three components to a solution of this problem. One is detection, that is figuring out that you're under attack at all, which is not as simple a problem as you might think. Localization, which is finding out where the attack is coming from, and then some countermeasure. And I'm really only going to talk about localization right now, but the other two problems are very, very serious and necessary for any real solution to this sort of problem. So the reason localizing attacks is difficult is the internet architecture today fundamentally permits anonymity. The IP source address is strictly written as on a voluntary basis, and as I like to say, much the same way as a kidnapper, when they send in a ransom note, they tend to not write their true return address on that ransom note. People attacking the internet tend to not write their true IP address on those packets. And you know, if everyone put in ingress and egress filtering, that would solve some of this problem, but I'm pretty dubious about that. I think this is a problem we're going to have to live with for some time. So using these false source addresses, packets escape into the network, and one of the great advantages of the internet is its stateless design, which here turns out to be a hindrance, because once one of these forged IP packets has hit the network, its origin is absolutely anonymous. There are no audit trails for you to go back and figure out where these things came from. And so the challenge is to figure out how can you trace attacks back towards their source. And this is valuable even, so I like to distinguish between the forensic uses of traceback, which is you want to find the guy and take him to court and so forth, and the operational uses. And from an operational standpoint, it's valuable to be able to trace back attacks, even if you don't get all the way to the attacker, just so that you can install filters in the appropriate place so your customer can go on serving content. So the rest of my talk is basically broken up as follows. I'm going to explain a little bit more formally the kinds of problem I'm talking about. I'm going to look at the current approaches that are available today for tracing denial of service attacks, and then we're going to talk about some other proposals that have been made to ease the problem. So what I call the operational traceback problem has a small number of basic elements, a number of attackers listed here. A sub 1, A sub 2, A sub 3. There's some routers in the network and some victims. And there's what we call an attack path, which is simply the set of ordered routers between the attacker and the victim. And the goal of traceback is simply to find that attack path, the set of routers that an attack must traverse through in order to reach the victim, places you could install filters in order to mitigate that attack. So the current state of the practice today is what Robert Stone termed input debugging. This is basically log input on iOS boxes, and other boxes have equivalent features. And the way this works is if you're under attack, you'll call up your ISP, you'll say, hi, I seem to be under attack, and the attack has such and such a signature. And hopefully a signature is something that can be well described as a bitmap, or like it's SINs or something like that. And you'll install a filter in your router, and all the packets that match that filter, you'll say, please log the input on which, the input port or MAC address on which these came. And then you'll take that input port and you'll manually match to what the upstream router is. You'll say, well, I'm getting 200,000 packets that came in on interface 6. Interface 6 is connected to this other router. Then you go to the next router and you repeat the process until you get outside of your administrative domain, and then you try to call the upstream ISP and convince them that it would be in their best interest, even if not in their economic interest, to aid you and so forth. And this is really how traceback happens today, and is roughly detailed in this web page out there. And this is, to the best of my knowledge, how most of the tracebacks that you ever read about take place. It's very time-consuming and really doesn't scale to more than, sort of single-stream denial of service attacks. So you have the effort and time of your own person within your ISP is a limitation. The inter-provider cooperation problem, I think, is really a showstopper here, because it requires a lot of different ISPs to work together for you to trace back to any meaningful distance. There have been some efforts to automate the inter-provider overhead. That is the time that your operator spends typing things. So there's an old tool from MCI called DOSTrack, which I believe is defunct, but used to try to basically log into your iOS boxes and do this kind of stuff for you with some Perl scripts. And there's a new proposal that Robert Stone at UUNet has made called CenterTrack, which attempts to automate it using BGP tunnels. And he has a paper coming out in the Usenix Security Symposium detailing his proposal on doing this. The other problems you have to deal with in some architectures, you have some significant router overhead for doing input debugging. It depends a little bit on the design. It fundamentally requires all the ISPs in the path to participate. You can't trace past an ISP that doesn't want to participate. If someone further upstream towards the attacker wants to participate, they can't really help, because you have no way of knowing, when you went from Sprint to UUNet to AT&T, if UUNet didn't want to play, you'd have no idea that AT&T was the next hop you needed to trace through. And finally, you really need to observe the attack in progress for this kind of approach to work. If the attacker stops attacking, well, end of story. He can come back later after you've given up, but the previous information he's put together really doesn't help you that much. So another approach that Hal Birch at CMU and Bill Cheswick at, at Lucent, that's right, they're Lucent, came up with is what I call controlled flooding. And this is something you can do with no involvement whatsoever from your ISP. And it's incredibly dangerous. But here's how it works. You create a map of the network using a set of trace routes or so forth. You have some idea of local or sort of moderate topology. And you have some, what I'll call helpful upstream hosts. And in this case, helpful means that they have not plugged some security holes. But maybe they're really helpful. Maybe they really want to help you. And so the basic idea is that you're going to load each upstream link from the victim iteratively, and by coercing these helpful hosts into sending traffic across that link and thereby overloading it. And what you'll notice is that if you overload a link that is on the attack path, the traffic that you are getting from your true attacker will be perturbed, because it will be competing with this overflow of traffic that you have intentionally sent. And so that means, oh, that link is part of the bad path, and you can follow it back, and you repeat until done. So, for example, here's some examples of how you would do this. In the example here on your left, there's some helpful host to H1, and you get it to send traffic across a link between what is that, R4 and R2, and that's not on the attack path, and so you're not going to see any perturbation in the attack coming from A2 because they're not competing at all. However, here on the right, H2 goes across the router, the link between R3 and R2, and it will in fact perturb the traffic, and it drops off, and you say, okay, that link is in it, so now I'll go and look upstream of there. The drawbacks of this are, it requires a map of the network. That's not so bad, but it requires fundamentally abuse of upstream hosts. And even if it's not abuse, it is in and of itself a denial of service attack. On the other hand, it has been used successfully. This actually does work if someone is really desperate, particularly if you're a shadowy organization. You can do this, and you can actually find out what's going on. It becomes harder and more expensive on high bandwidth links, because the amount of perturbation you'll get you have to be able to source more traffic to perturb the attacker in a way that you can actually tell that the attack is going across that link. And it's also not well suited to distributed attacks, because as soon as you have multiple different edges contributing to the attack, it becomes very hard to make that differentiation simply by adding more noise into the signal. But it has the huge benefit that it doesn't require providers to be involved from the standpoint of the victim. So there are some recent developments. Those are the two things you can do right now, more or less. The recent developments are proposals for modifying the way routers work. Generally things that make small changes to the forwarding path, and in order to enhance traceback capability, and to either reduce or eliminate overheads on ISPs in doing traceback, to allow traceback to be done post-mortem, that is after attack is completed, allowing partial deployments, and fundamentally they all seem to use probabilistic path reconstruction. I'll explain what that means. But the caveat is that all of this is work in progress. You're not going to find something that works completely in any of the presentations, any of the things I'm about to present. So Steve Belvin has a draft spec for something called ICMP traceback that is an example of these. And the idea is that you sample packets in a router. So roughly, let's say every 20,000 packets that come through your router, you'll pick out one of those packets and you'll generate a special ICMP message that you'll wrap around the packet, which will include some information about the forward hop and the reverse hop, some authentication information, and then as much of the origin packet content as will fit, so you can match this special ICMP traceback message with the actual data traffic. And the idea is that a flood, even though you're sampling very few packets, you'll get enough of these that you can subsequently reconstruct the link. Oh, that's nice. That is charged. And the other little special thing that you do here is when you send these ICMP messages is you'll set the TTL to its maximum. And the reason that you do this is because that allows you to slightly improve the way you can reconstruct the path, because it means that the TTL will always decrease monotonically in sites that are further away from the victim. So the closest router to the victim will be sending traceback packets with a TTL of 254, and one further away will be 253, and so forth. It's something that can't be spoofed because all the routers are going to decrement the TTL. So the idea is that you get these ICMP messages at your victim, either at your demarcation firewall site or maybe actually at the victim host. You'll pick these up, and they'll each represent a sample of your path. So there'll be, one of these ICMP messages that will reflect a particular router link, and another one that will reflect the next router link, and so forth. And you'll use the TTL to order these different packets, and then you'll try to match the forward and reverse interface information. And there's a draft on this that is in very early stages. There we go. So the limitations of this approach right now that we're aware of, one is there's this ICMP problem, which is that, ironically, at least in part in response to denial of service attacks, people are increasingly filtering and rate limiting ICMP in the network, which is a pretty new thing. It used to be that people only did it at the edges, but now there are providers who are just cutting off ICMP that aren't from their direct peers. So ICMP may not be, protocols based on ICMP may not be working too much longer if people continue down this path. The other problem is because of the way the forward and reverse path information is specified, it can be pretty hard to deal with partial deployment in these schemes, because when you get a discontinuity, you say, well, previously I was on interface 6 for some upstream router, and then you don't get any more, there are no more messages for 5, 6, 7 routers. There's no real way for you to match those two together, and understand that those two messages actually constitute consequent routers in the same attack path. And then finally, and this is probably the most problematic, and it's problematic for all the schemes, is that ICMP traceback is fundamentally vulnerable to chaff. That is, that an attacker can generate these false traceback messages that say things about where the attack path is that aren't quite true. And so in order to deal with this, it requires an authentication infrastructure with some kind of forward security, so that when you send out these messages about that, here is a such and such part of the path, it requires some authentication information that's constantly changing, and then you go back and query and say, did this thing really sign it? And that itself is a problem for denial of service attacks, because if your routers now need to be going and verifying signed secrets all the time, then someone could just simply hammer on your router. So this is sort of an open problem that the people working on Traceback have not yet come up with a solution for. There's another technique which myself and some other people at UW came up with that's appearing in the next SIGCOM, and it's called packet marking, and it's very similar actually to ICMP Traceback, except the distinction is that you don't generate any separate messages. You encode the data that you need in the existing packet. So again, you probabilistically mark packets in routers. So with some probability P, you go and mark this packet and put some information about that particular edge in the attack path, that particular link in the packet. And we have a couple fields. Ignore for a moment entirely where I get these fields. Pretend they're there. I'm an academic. We'll deal with that in a second. So there's one field called an edge field, has 2 adjacent router addresses, and another field called a distance field, which is the number of these edges, the number of links between routers that are actually participating that have been traversed since you marked the packet the first time. And so this serves the same function as TTL. So if the packet isn't marked, you increment the distance. If you mark it, you set the distance to 0. That way, that distance field always represents how many hops since the packet was marked. And no one can spoof that. No one can make a false distance field any closer than the attacker actually is. And then, the reconstruction is similar. You collect these packets. You have a bunch of edges. You construct a graph. And here's a funny little formula on the bottom that says how many packets you need to reconstruct the graph. And it's actually really easy to understand, but I'm not going to waste people's time. It's not very big. That's the bottom line. You don't need that many packets. Now the practical problems are that I don't have those fields. I need 72 bits to make this thing fly. So we came up with a bunch of really hairy, ugly encoding tricks to try to fit all this data into the existing IP header via overloading what we feel is a horrendously underused packet header field. And we're going to do actually, before I get there, we're going to do a couple things first to shrink the amount of information that we need, and then we're going to fit everything into 16 bits. So the first thing we're going to do is we're going to compress all of the edges using XOR. So I had these edges that said, all right, I have traversed between router R6 and R5, or here, R2 and R1, or I've traversed between R3 and R2. And I don't really need to send all that information. I don't need to send the full edge. Instead, I can send the XOR of the 2 adjacent edges. And so what will happen here is, normally I would send a message. There would be, let's see, 4 different messages that I would get. One with R6 and R3 in this whole attack path here, one with R3 and R2, and so forth. But by just sending the XORs, that's actually sufficient information because I'll get, I guess I can use this pointer. I'll get R1, the last router before the victim, will send a message saying, all right, so the last thing came from R1, and then upstream it'll send R2 XORed with R1, and R3 XORed with R2, and so forth. And then you can just sort of unwind this because XOR has this great commutative property and reconstruct the entire path from the XORs. And that shrinks the space by a factor of 2. And then what we can do is, that's still only get this down to, 32 bits or something like that. And so we'll divide those XORs, what we call edge IDs, into chunks. We're going to essentially fragment it. And then so when you mark a packet, you'll pick one of those K parts of that 32-bit thing, and you'll send that. And that increases the number of packets you need to get, but again, not by much. I'll give you some empirical numbers. And then we do some stuff because the chunks may not be unique, and you use a hash to validate that, in fact, things go together. And there's a paper that describes all the details. In terms of how we actually encode this, we're going to overload. The proposal was to overload the ID field. The observation being that, at least on the links that we have gotten measurement data about, there's very little real fragmentation out there because you'd be nuts to send real traffic fragmented because your performance goes through the toilet. And so in 99% of the time, that field's not used at all. So we have a really ugly scheme for dealing with fragments. It makes it bad. People who use fragments a lot won't like this. However, if you don't fragment a lot, we can actually fit everything in the 16 bits in the ID field in a way that lets you reconstruct the entire path. And so we actually built a system and this is basically results for reconstruction time for various path lengths, and it's on the order of a couple thousand packets to reconstruct a path of just about any length, and when you're dealing with the kinds of attacks that Yahoo is dealing with, that's a fraction of a second. So in that sense, it's reasonable. So limitations of packet marking, breaks fragmentation. Fragmentation, it'll still work with fragmentation, but it significantly degrades fragmentation worse than fragmented flows were before. It can also break IPsec because IPsec wants the authentication header wants to cover the ID field. So that's a problem. The current algorithms that we have in the paper don't scale very well for large distributed attacks, dealing with hundreds of sites. And as with the ICC traceback message, it's vulnerable to chaff. You still need some kind of forward authentication scheme, and that's a real problem. So other possible approaches that either have been proposed or people have thought about, there's just doing distributed analysis of packet counts using netflow stats. People exchange netflow stats around and say, look, here are where the big flows are coming from, and this is where the purported, and the sources don't seem to match up, and they came in on this interface. And you can pretty much, in theory, put that together in a way that you can trace the attacks back. You can actually do packet logging using something like Coral, where if you have a good implementation of port mirroring on your router, you can actually do sampling and do some logging and match things up. This is a pretty hairy database integration problem, but this is doable. And then there have been some unpublished proposals on doing what I call low overhead audit trails, where you'll take a packet and you'll hash it into a bitmap on the router. And you'll subsequently go back to the router and present them with the packet and say, is it possible that this could have gone through there? And they'll say, well, there's a 30% chance. And then you go back to the previous router and you build up with reasonable certainty that particular packets went through particular paths. And then there are hybrids of all these approaches. Now, as I said before, traceback is really, you solve the traceback problem, you still have some very big problems left over. Detection, how you know that you're under attack is actually a really big problem. The guys at Yahoo were spending several hours during their attack thinking that their router was crashing, and they kept rebooting their router. It is really a problem understanding. And then once you figure out that you're attacked, how to identify the attack in a way it's meaningful, that it is distinctly identifies the attack and doesn't identify your customer. Because there's not really, what distinguishes the Victoria's Secret homepage from a place under attack? Not much. They're getting a lot of traffic. All of a sudden, it's very popular. Someone could build an attack just like that. And then once you've been attacked, there's the issue of, what do? You need again this very good identification so that you can filter the attack but not the customer traffic. And right now, I don't think there are a lot of really good capabilities in this space. And getting this to work in an inter ISP context where you want someone who's not receiving any money from you to actually install a filter, this is a real challenge. So in conclusion, basically the schemes we have today for IP traceback are pretty straightforward, but they have pretty high overhead and don't scale. We're going to need something else to deal with this problem unless the hackers give up. So there are some new proposals that are better, but they're not perfect, and they're going to require changes to the network infrastructure, so they are not going to be here. They're not going to be here in 6 months. And even once you solve these, sorry to give a depressing talk, but there's a lot more to traceback than just, there's a lot more denial service than just dealing with the traceback problem. So there's a lot of technologies that are going to need to be developed to do this. And little postscript, as a consequence of some of this work, UW has a spin-off. It's about 4 professors doing denial service management solutions for ISP, selling stuff to folks to deal with their denial service problems. It's ask the networks if people are interested. But with that, I'll take any questions that people have, if any.